Hello, this is a talk that I gave in October of 2024 to the Automated Mineralogy User Group meeting, and it covers extracting mineral chemistry from TIMA, which is an automated mineralogy technology based on SEMs, and how you can use it for machine learning applications. So this was developed during the Indicator Minerals for Nickel Sulphide Exploration project, which was sponsored by Mariwa and a bunch of industry sponsors. Our goals were to outline the chemical signatures that indicate sulphide mineralization. And when we're doing that, we were also looking at developing new tools for rapid analysis of these indicator minerals, which is how we stumbled upon using TIMA for mineral chemistry analysis. The project had 1,150 samples based mostly in Western Australia, but also supplemented with globally renowned nickel deposits from around the world. We have komatiitic nickel deposits, lateritic nickel deposits that are based in intrusions, as well as layered intrusions of spinels and barren samples as well, which contain no sulphide mineralization. We also looked at some greenfield exploration to understand when we're measuring these mineral chemistries if it can be practical in a greenfield exploration program. When we collected all of our samples, we split the data up into mineralized and unmineralized samples. If the sample came from anywhere within an intrusion or a flow that we know that contains massive sulphide or nickel sulphide, we call it mineralized, even if the sample itself does not have nickel sulphide in it. And then anything that is external to the sample, including the host rock or intrusions or flows that contain no known mineralization, are called barren for this purpose, or unmineralized. So now I'll go through the data collection using TIMA and the data distribution accuracy of the quantification using TIMA. So these are our mineral maps that you may be familiar with. Here we're focusing on spinel. So the spinel are in reds and purples. So you can see the little chromites in there and purples of the chrome magnetites here. This is within a serpentinized komatiite, and this is in basically a gabbro intrusion. We also looked at magnetite, which is part of the spinel family. Magnetite can crystallize straight from a sulphide liquid. So this is magnetite with chalcopyrite, pyrrhotite, and pentlandite. Or magnetite can also crystallize from the silicate liquid. So this is magnetite with amphibole and pyroxene. We also have some zoning that occurs in these spinel, which I'll go through in detail a bit later. So when you are quantifying minerals using the TIMA, you have to be a bit wary of exclusions or inclusions or things that are smaller than your step size. So in a lot of the cases, our magnetite analysis have exclusions of ilmenite throughout them. This is too small for the TIMA to pick up when we are just stepping at 12 micron step size. So when we quantify this grain, those titanium phases will be incorporated into the analysis. For this case, I think that it's okay because this was the original magmatic composition of this magnetite. It had this titanium in the crystal structure, and as it cooled, it exolved out of the crystal structure. So in this case, I believe that it's okay, but it's something that you should be wary of when using this technology. We ended up with about 42,000 TIMA EDS analysis, and a lot of these mineral grains were zoned. So you can see in the previous image and this image, almost all of the spinel grains have some sort of zoning. So we decided to separate those zones into different chemical phases. So we have chromites, chrome spinels, and magnetites, and each of those zonations are split up into their chemistry. So when TIMA is quantifying each grain, it will quantify it by these splits in the chemistry as well. So you have to be careful with your TIMA library as to where these chemical splits are occurring. So the way that we quantified the spinel was we liberated our phases. So we collected the data in modal acquisition. We liberated them to get a liberation analysis, which allows each of the grains to be recognized as a single unit. You can then export the EDS spectra summed across that entire grain and open that in Spectrum Tools and quantify it. Anything that is less than 20,000 counts does not get quantified in Spectrum Tools, so you have to filter out anything that is lower than 20,000 counts. So Morgan wrote a Python code to do this, so it just looks at the total count in the spectrum and filters out anything that is lower so that we don't import it into Spectrum Tools and make sure that everything we do import into Spectrum Tools can be quantified. After quantifying all of the spinel, you can then go back into the grain viewer and export the X, Y, and size information for each of the grains and then tie that information together so that you have the chemistry of each mineral grain tied with the XY coordinates of its location in the sample and maybe its grain size as well. So this took a very long time. It was, if I tried to import more than about 1,000 or 2,000 analysis into Spectrum Tools to quantify it, the software would have a really, really tough time. And also they wouldn't give unique grain IDs, so it was difficult to give the XY coordinates for each grain back to the quantified spinel values. So we ran into a few speed bumps there. There is a new way to quantify grains. It's not released yet, but I was happy to be a beta tester of this feature. So the new workflow would be to liberate your phases if you collected it in modal mode. And then there's just a button that's auto quant. So you click auto quant, select the phases you want to quantify, select the elements you want to quantify, and then it just quantifies it all for you. You can then go into Grain Viewer, export that data along with each of the XY coordinates and size and all the other grain identifications that you need. And this is, I would assume, about 10 times faster than the previous workflow. The way that we were doing it previously was almost impossible to do practically during the day. I would usually leave it overnight and find that the software had crashed halfway through the night, and it took me weeks to quantify all of the spinel grains in our 1,150 samples. But I have since done it again using this auto quant feature, and it just took just one little overnight session. So it is much, much faster and much, much easier, which means that more people could maybe use this data for machine learning applications. So looking at the quantification compared to the gold standard, which is of course EPMA or microprobe, I looked at some olivines and measured the exact same spot on the EDS as I did on the EPMA, and it looks pretty good for olivine within error for a Forsterite 88 olivine grain. For our spinel, we do have a bit of noise. Our magnesium is maybe overestimated, our aluminium is maybe underestimated, and when we get to lower concentrations of stuff, there is a lot more noise. There are two ways that you can quantify analysis. You can do the oxygen by formula, which is where you specify the formula of the mineral and it calculates the oxygen based on that, or you can measure the oxygen. We did both and had a bit of a look at the spinel quantification compared to EPMA again, and you can see the oxygen by formula is a little bit high in the chromium content, and we couldn't really figure out why that was. Again, when we're looking at some different chemistry of the spinel, so now looking at aluminium pore spinel, when we have the oxygen by formula, a lot of the chromium is increased, and we couldn't really figure out why that was happening, so we chose to move forward with doing measured oxygen. So you can see the data is a bit noisy compared to the EPMA, but it is in the same region. We don't have that push up of the chromium values. So we thought that that was a better way to proceed for all of the data I'm going to talk about in the future. So back in 2001, Barnes and Roeder published a bunch of spinel chemistries and compared them to their host rock types. This is their original data with some contours drawn around it. And you can see that our komatiitic samples are very similar to their komatiitic samples. So in this spinel ternary, where we have the atoms per formula unit calculated for aluminium, chromium, and iron 3+, you can see our samples exist in the same region as their komatiitic samples. So this is looking really good as for spinel being an indicator of host rock type. If we look at layered intrusions, the Barnes and Roeder 2001 data has a lot of samples in this sort of high chromium, high aluminium section. We also have a lot of samples in that high chromium, high aluminium section, and we found that the high pressure intrusions also have this high aluminium signature in their spinels as well, which you can see in the Barnes and Roeder data. So this is looking like these major elements have the potential to be host rock indicators when using spinel as an indicator mineral. So now moving on to our machine learning. So we ended up with a lot of data. We ended up with 102,000 TIMA grain analysis, 20,000 laser ablation ICP analysis, and you can see that most of the laser ablation analysis, at the very least, is concentrated on spinel. So it was the main focus of this study. It is easy to measure. It's very common in these intrusions and flows, and also it survives in the weathering profile. So it would make a really, really good indicator mineral if it was an ex-situ mineral. So most of the features that we're trying to predict are at sample scale or larger. So we want to know if the mineral that we're analyzing came from a deposit that contains nickel sulphide. So it's a problem of scale here. We used the data that we had to categorize each of the analysis into mineralized or unmineralized, and allowed the data to be split into a testing set and a training set. We made sure that any sample, so rock sample that was in our testing set wasn't also in our training set, because the machine learning models have a tendency of finding those sorts of shortcuts through the testing and training. So any rock sample that is in our training set is not also in our testing set. So the best way to check if the models are working is to check their recall. To do that, you can use a confusion matrix. So if this model was predicting the true class every single time, it would be a completely perfect model, and both of these diagonal boxes would have ones. The amount of offset of this number gives you an idea of the indication of like false positive and false negative analysis. So this gives you an idea of how confident you can be in the prediction that these machine learning models are making. Once we make the machine learning models, we can then interrogate the results. We can look at how well these models predict the mineralization using that confusion matrix. We can see what elements are being used to make those predictions, whether or not those elements make geologic sense. So when looking at our spinel database, which was by far our biggest database, you can see that the recall is pretty good. We have about a 75% confidence in the prediction just using the major elements and just using TIMA data. So you can see the chromium, titanium, and vanadium contents are the most important to make those predictions. And this means that spinel would be a really, really good indicator of magmatic sulphide presence. So it would be a really, really good indicator for exploring for nickel in any region where you can find a spinel on the ground. We also looked at the trace elements of spinel using laser ablation ICP-MS and also ran them through the machine learning models. We found that using the trace elements in spinel, we can have an okay idea at what the sulphide volume at sample scale would be. So this is using the TIMA data on a 25 mil round, calculating the volume percent of sulphide in that round, and then analyzing the trace element chemistry of the spinel in that round. And it was able to have a pretty good idea of how much sulphide was around in the sample. So this means that spinel might not only be a good indicator of sulphide presence, but it may also indicate the volume of sulphide that is present. So we could start looking for bigger nickel sulphide deposits rather than the small ones. So now that we've made our machine learning models and we're pretty sure that they work because that recall is looking pretty good, we can apply them to a prospectivity problem. So back in October of 2023, Geoscience Australia and Curtin University published the heavy mineral map of Australia. So this is minerals that were collected in stream sediments on the surface of Australia, almost across all of Australia, except for northern Western Australia there. And they analysed all of this data with TIMA. So because our machine learning models were built on TIMA data, we can use our machine learning models on this TIMA data. So looking at the chromite content of the heavy mineral map that was published by Curtin University, you can see that there is a lot of chromite in Queensland. In Western Australia, where we know there are nickel deposits, you can see there's a couple of hot spots for chromite, but apart from that, it's not looking super promising for using chromite to understand where the nickel is. So if we just focus on Western Australia, we can use our machine learning models to make a prediction of where is the most prospective for nickel in Western Australia. And the good thing about Western Australia is we know where it is prospective for nickel because there are a lot of nickel occurrences and nickel mines in Western Australia. So all of the nickel mines and nickel occurrences are shown in little blue boxes in the background. And then we ran all of the heavy mineral map of Australia spinel data through our machine learning models. And then it gave a flag as to mineralized or unmineralized. So if the proportion within that sample is highly mineralized, it will be a very deep red color. If it has a lot of mineralized flags of spinel in that sample, it will be a big dot. So theoretically, if we are near nickel sulphide bearing intrusion, will have a really big red dot. So you can see up in northern Western Australia here, we have lots of big red dots which correspond to the nickel deposits there. We have lots of big red dots and big dots just generally in the Kalgoorlie region nickel province. We also have some big red dots that are associated with the New Julimar find next to Perth here. And then we have some big red dots up in like the Coral Bay area, which are not associated with a known nickel deposit yet. We also have a couple of big red dots down in the Nullarbor here, which is under very deep cover, but looks like it could be prospective for nickel sulphide as well. So that's all I have to tell you about today. This is the summary of what I've talked about. So extracting mineral chemistry from your TIMA data gives you more value out of your TIMA data. So this doesn't require extra machine time. This is all in your data already and you can extract it very quickly. Then you have very large, robust, consistent data that you can use in machine learning models. This is about 10 times faster than it used to be, so I recommend giving it a go. But some things to keep in mind is that you should always compare apples to apples. So right now, comparing TIMA data with other TIMA data looks pretty good. If you were comparing all of this TIMA data to EPMA data, just use a little bit of, take it with a grain of salt. You should also take care when you're working with chemical zonation, which can occur in many crystal phases and grains, and also inclusions and exsolutions, which can edit your mineral chemistry as well. So if you want any more information, please visit our website. Thank you.